So we can continue here this lecture about explosion protection, and now we will focus on dust explosions. Here, this I have shown you a grain dust explosion or a sugar dust explosion. So dust explosions occur quite frequently, at least in Germany. But often, or normally, we have measured to avoid the consequences of such an explosion. So if you use filters, there's maybe an explosion in the filter, but then there is some pressure relief. The explosion pressure can leave the system, and we will just continue with the process. Dust is here better to handle. However, of course, you see, it's important to consider the consequences of such an accident. So even though sugar, something which looks not dangerous for us, can burn as a dust, and then we have these fatal consequences. So what is dust? So dust means small solid particles in the atmosphere that settle through their own weight. So after some time they will finally reach the bottom, but they remain in the atmosphere and form a dust-air mixture. So they normally are quite small. The maximum particle size does not exceed 500 micrometers. And so all dusts which form flammable dust-air mixtures are dangerous. So you see here an overview from Germany. So grain dust, wood dust, plastic, metal dust, coal dust, paper dust. A lot of accidents has here occurred. And a lot of different ignition sources are important here. So mainly mechanical sparks, static electricity, electrical equipment, welding, and so on. So most of them are also valid for flammable gases and liquids. But we have also something here like glow nest. So we have somewhere deposition of dust, for example, aluminium dust, and then there's some liquid. So we have an aluminium water mixture. So some reaction may start here, take some time, it starts to glow, and then this glow nest may fall down into the pipe system again, reaches the filter, and suddenly you have a big explosion. So there is a horrible example from China, where they used to polish aluminium tires, and so such a glow nest then leads to a devastating explosion, and aluminium burns with 3,500 K. So I think 75% died immediately and 75% died later due to the burning consequences. Of course, it's difficult to have a proper hospital system to take care of such a catastrophic accident. So when you deal with dust, you have to consider some additional ignition sources compared to flammable liquids and gases. Of course, we have the same concept here. We use safety characteristic data to classify our combustible dusts. And here we have, in addition, also the characteristic of deposited dust, but because mainly these dust are laying on some surfaces. So burning behavior, smoldering temperature, spontaneous combustion are of interest. How fast does it burn on the surface and so on. Then these dust layers, if they are heated, so that if they layer, for example, above an electrical motor, they're heated from the surface of the motor, do they produce flammable gases? Carbon monoxide or other hydrocarbons, for example. And so we have to check the flammability of these smoldering gases. And finally, we have the characteristic of the welled up dust debris. That means the dust air mixture we have to consider. And here we have several quantities, so it's more or less like with the flammable gases and liquids. So we also have explosion limits here. We have an ignition temperature, but the two most important criteria here are the maximum pressure rise, the KST value, and the minimum ignition energy. So these two quantities are normally used to classify our combustible gases. So a very important parameter, of course, is the particle size. So iron, as a big block of iron, does not burn. But if you have fine iron wires and put it in an oxygenous atmosphere, it directly starts to burn. It depends, of course, on the surface to volume ratio. So the surface area increases exponentially with when the particle size decreases. So fine dust react more strongly than coarse dust. So an important value is here the median value for the average particle size. So 50% by weight of the dust is coarser, 50% is finer than the median value. So for a safety assessment, it's not important just to know, okay, I have aluminum dust here. You also have to know the particle size distribution for safety measures. So here we have the explanation for this. So if you have a cubic centimeter particle here, you have a surface of 6 cubic centimeter. If you have here the same, I think it's 4 times 4 times 4. So I think 16 particles here, same volume, but of course much larger surface area. So when we look at the burning behavior, there are some classical tests. You have here the line of dust, and then you have several ignition sources which you hold at the end, and then you just check, does it start to burn and how fast does it burn? And so you classify your substances here. So you have something like salt here, no burning. You have something like explosives here. If you ignite them, of course, they burn very fast. Smoldering temperature, as I said, it's important because we need to know, does the deposit layer of these dust smolder, and at which temperature they start to smolder. So you have this dust layer here, and you just put an hot wire system on top of this surface, and you just check, does it start to burn or not. So now coming to the important quantities. So maximum explosion pressure. Here we have a system, so this is an old classical setup, 1 cubic centimeter vessel. We have an vessel for the dust layer, or for the dust, sorry. So, and this vessel here has an overpressure, so you open a valve, and then through this ring here, we have some holes. We blow the dust into the vessel, and after a given time, then we ignite the mixture and measure explosion pressure and pressure rise. So here you see the temporal diagram of the setup. So in the dust depot we have an overpressure here, 20 bar. We open the valve, the pressure reduces, and of course we can adjust the timing. Here the ignition is at the end of the dust deposition, and in the explosion vessel then we see after ignition a pressure rise due to the explosion. This of course depends on the mixture composition. So we have a maximum explosion pressure for different mixture composition, and for one specific dust concentration we yield a total maximum value. So this is then the value we need for the safety assessment. And the same we see for the pressure rise. It also depends on the mixture composition. Therefore, we not just have to perform one experiment with a given dust. Of course, we have to vary here the concentration. Then, of course, it depends on the type of dust. We see the same effect here. We have dusts which burn quite slowly. So cooling effects are here of importance. They have very low flame velocities, so slow pressure rise and low maximum pressure here in case of iron. And this of course then change if we consider aluminium. Here we can reach much higher pressures, and we have a much faster pressure rise. So finally we use the concept of a KST value here. And this is together with a minimum ignition energy the most important value, at least in Germany, if you consider flammable dusts. So we have here several dust classes. So dust class 1 has the smallest KST value, and the critical class, dust class 3, we have 300 bar per second. So I've checked literature. I was astonished. Also in English literature I found this KST. So KST stands for Staub, German for dust. So I'm not sure if it's a concept only used in Germany, but this seems to be also used in other countries too. So dust also have explosion limits. There is of course a lower explosion limit, which is normally in the range of several gram per cubic meter, and we have an upper explosion limit which is in the range of several kilogram per cubic meter. And for me it's always astonishing when I look at these two optical experiments. So if we have a dust density of 30 gram per cubic meter, so which is quite here in this range of the lower explosion limit, we cannot see a 40 watt lamp after distance of 1 meter. So we already have a very dense atmosphere. And the other example here, 50 gram, again in this range here, a light loss of 50% occur after 5 centimeter. So these are already quite dense mixtures. And one final example, which maybe should remember, that we have to clean our houses more often. If we have a dust layer of less than 1 millimeter here on the floor of a combustible dust, and we will whirl it up, then it's sufficient to fill the room with an explosive mixture. So for me, this is contradiction here. I'm not an expert with dust. This seems to be very less, and it's astonishing that this already gives us such an dense dust-air mixture. And so you have seen this Hartmann tube before. So the experiments are performed here in a similar way. We have some dust here, then we use some pressurized air to whirl up the dust, and then we start a quite strong spark with an energy also in the Joule range, and check, can we ignite the mixture, yes or no. So typical setup. After an explosion, this opens, pressure relief, then it closes. We can clean the setup and perform the tests again. Minimum ignition energy is the second most important quantity. We have the same concept here. We have some energy stored here in a capacitor, and the energy here is then again depending on the capacitance and the breakthrough voltage we have, finally leading to ignition. And we have again a similar concept. So we have a dust layer which is then whirled up by by pressurized air. And so of course this depends on a lot of quantities. Therefore, if you check literature, always be careful. It's not the one value you can find. As we have seen, the particle size distribution, for example, is very important for this. But mainly the usage here, we have 4 categories here. If we have a minimum ignition energy below 1 millijoule, so the most combustible gases in group 2A have an energy, I think it was 0.2 millijoule, above 0.2 millijoule. So here we are already in the range of the ignition energy of hydrocarbons, of a lot of hydrocarbons. But this goes up to over 100 millijoule. Also an example here is wheat flour. Nevertheless, wheat flour is quite common dust. A lot of accidents occur also with wheat flour, even though it has quite high ignition energy. But these are gives us a classification, and together with the KST value, based on these 2 values, we can select proper safety measures for a safe operation of our system. There's only one slide for hybrid mixtures. There is some ongoing research also at PTB for this topic, but it's difficult to discuss. So for example, in mining areas, so we have, I think I've given the example yesterday. Of course you have coal dust, but normally this coal dust is not so critical. And most often you have a layer of coal dust, so not a dust-air atmosphere. So this is quite easy to handle with respect to safety. But if you then find a methane pocket below, and you suddenly have a methane air atmosphere, this is much easier ignitable, and then you have a local explosion event which whirls up your dust layer, and then this dust air mixture can start to react because you have sufficient ignition source. And then you have, of course, below in mining you have long tunnels, and that means you whirl up the dust along these tunnels, and then finally you can reach detonation. And it's astonishing to see what such a detonation is doing with the heavy equipment in mining areas. So they are totally deformed. And of course you can think, if there is a human being in way of such a detonation, there is no chance to survive such a catastrophe. So it's important to know this influence, but it's difficult to assess safety here. Because one, the gas explosion can influence the explosion behavior of the dust mixture, and the other way around. So the dust mixture may change the ignition or the flammability limit of the system. So normally we try to avoid this, to have hybrid mixtures. We have either explosive gas atmospheres or explosive dust atmospheres. And we try to avoid to have a mixture because it's always difficult to assess safety here, and a lot of additional work is necessary. It can be done, and there's some ongoing research, but again, it's quite difficult. So with this, I would like to close this session. So we have had a short discussion already before we started this, but so maybe we can continue it. So you have any question concerning this part here? So, okay.
How to decide it is explosion or it's burning? Is it based on pressure data or something else?
Okay, what is an explosion for you? What is a burning event?
Yes. How to distinguish between
It's
this?
so in German we have the word Verpuffung. I haven't found an English expression for it, even though if I use deep L, it always gives me explosion or deflagration. Explosion means we have a sudden change in temperature and pressure. So this is maybe something we can use. So if there is a pressure rise only of 5%, there is some combustion. Of course, there is some pressure rise, but if it's below 5%, we say this is not explosive.
How to decide that number?
We use standardized methods. So as I've explained for the explosion limits, if we use this bomb method, we ignite in the center of the bomb. If the pressure rises below 5%, then we consider this as not flammable.
No, my question is why 5%? Why not 6%? Why not 4%? Why not 10%?
Well, you have to use a number. You have to use the limit. So the idea of the standardized method is we have to perform thousands of experiments for thousands of mixtures, and we don't know all the chemical details here, the reaction mechanism, so we cannot calculate it properly. Therefore, we just have threshold value, and until no accident occur where we see this threshold value is not okay, so we have to be stronger or stricter here, then we use this threshold value.
Is that 5% limit is same for all the fuels? Suppose, for example, coal dust, normal dust, sawdust. So is that 5% is same for all, or is it different for fuel, different for the dust.
So this is for the flammable gases and liquids. First of all, this 5% criteria. For dust, I have to look in the standard too, so I don't know which criteria they have there. So, and then, of course, you have to check the standard carefully. Are there different classes? Huh? So sometimes there are something like, okay, you see you need this energy, then you can increase the value maybe. But it depends on the standard.
My next question is related to that dust class only. So what does that dust class mean? So it is related to size of the particle or?
No, so the dust, yeah, KST value. You mean this here, right? Yeah, this means just how fast is the pressure rise. So how fast are these dust burning? But of course, it depends finally what particle size distribution and what dust concentration they have used in such an experiment. So with dust concentration, this can be or is covered. Where was it? So this is normally covered, so we perform the experiment with the same dust at different configurations.
So ultimately it is depending upon KST, and KST is a function of dust concentration as well as particle size.
Yeah. So if you have to handle with a combustible dust, then first of all you can check literature. Are there any safety characteristic data for my substance here? So if you have aluminium dust, the property to find something is quite high. But if you have a new material, of course, there is no data. So what is mandatory in countries like Germany, before you start to work with this kind of material, you have to measure these data. And then finally, it's only valid for your specific dust you have. That means for your specific particle size distribution. So you cannot change your process, get another particle size distribution and use the old safety characteristics data. You have to measure it again. Okay. So we will close this session and continue after lunch. 3 o'clock? 3 o'clock? Okay, thank you. Number 27 of, or 20, yeah, 27 of 28 of lectures. So we are nearly at the end. Now we will focus on an application of all the work we have done today. We will then focus on I have mixed it, so tomorrow there will then number 3. So here we have combustion fundamentals of explosion protection part 4. So the application of all the theory of combustion for a specific problem, flame-proof enclosure, flame arresters. So what is a flame-proof enclosure? This is one of the oldest type of protection to have an explosion protected device. It was developed around 1906 in Germany, France and England from different scientists, especially for mining area. So the idea is to have an electrical motor or another electrical equipment. Here the terminal box, for example, and inside these enclosures you have an ignition source. So if there is an explosive atmosphere in your chemical plant or in mining area, this explosive atmosphere can enter the motor, and inside this equipment an explosion can occur. So there are two main requirements. This enclosure has to withstand the internal explosion pressure. We have seen in the morning how complex it can be. Not only 10 bar can be accepted, we can reach also 40, 50 bar explosion pressure inside. So it's a critical test concerning the mechanical strength of the equipment. And the other and more critical test, especially when we deal with hydrogen, gas group 2C, is the so-called flame transmission test. So such an equipment has a lot of different gaps. Here is a gap between bearing shield and housing. Here is a gap between the cap of the terminal box and the terminal box itself. So you have a lot of different gaps. You have specific requirements given by the standard, which you have to fulfill, but there's always a flame transmission test at the end. So even though your construction follows the minimum requirements of the standard, there will be flame transmission tests. That means you ignite inside this geometry an explosion and check in your test lab, is there a flame transmission, yes or no. So you perform this test at different positions, you ignite at different positions, and you repeat this test 3 or 5 times, depending on the gas group you are interested in. And this is an outcome of such a test. Here the flame is going this way from the inner side to the outer side. So the motor has failed this test and has to be redesigned and retested again before they can sell it in the market. Here we see such an example outside an explosion vessel. So here we have a foil, and inside this motor and outside this motor the atmosphere is filled with hydrogen and air, and so internally an ignition was initiated, and you see that there was a flame transmission here at this area, and then the outer atmosphere explodes too. So this motor was a special machine already sold. The motor has failed. It needed to be redesigned. It failed again. Needed to be redesigned again. So they could bring it in the market with some delay, which cost them a huge amount of money. And the problem is, of course, these tests, the certificate you need, always you can achieve at the end of the construction cycle. And of course they are blaming always the test houses that we need too much time. But in this case it was maybe not the error of the test house why this motor was not sold on time. So flame transmission, flame quenching, this is what we are talking about. Normally, so what we've seen here for a flame-proof enclosure, you have inside an equipment an explosion, and you want to avoid that there is an explosion of the outer atmosphere. So the flame has to be quenched in the gaps you have. No flame transmission should occur. The same is true for flame arresters. So if we have long pipes and if we want to stop the explosion in such a pipe, or want to avoid the development of a detonation, we have flame arresters in these enclosures and in these pipes, and then explosions start on one end of this pipe, and then it comes to such an flame arrestor. Here we see further details in the following, and the flame has to be stopped. So it has to be reliable protection against flame transmission, and of course high chemical, mechanical and thermal resistance, because it is in an aggressive, it may be installed in an aggressive atmosphere, and a flame-proof enclosure, for example, can be installed on oil rigs so we have a lot of salty water and so on. So the lifetime quality has to be assured. But at least for flame arresters, convective mass transfer should be possible. So in this pipe, you always have a mass flow in one of the directions. That's the main idea of a pipe, to transport fluid from point A to point B. So there should be not so much flow resistance due to this flame arrestor. On the other hand, it should stop a flame when a flame is coming there. So this is the constructive problem here. So how does quenching then occur? So Professor Sahu has also explained this on one of the slides. So when there is a flame and it's moving through a small gap, so first of all, you have cooling at the wall, heat losses. Then you have a stretching of the flame front. So if you have a large pressure difference between the two compartments, so between this side and this side, so you have seen in the morning there's always an acceleration through this nozzle, through this gap. So we can reach here the sound velocity of the hot gas. And it's like blowing out a candle. If you stretch the flame, you may blow it just out. So this can already quench the flame sufficiently. And then you have wall reactions. So radicals may be removed and destroyed at the wall, and then no longer can take place in the reaction. So, of course, it depends on the superimposed flow we have. So, you may find in literature the quenching distance as a factor. So 0.6 something for hydrogen millimeters. That is a distance when there is no superimposed flow interacting with the flame. So it's just the flame inside the gap. You have maybe a flow velocity equal to the flame velocity, so the flame should stay at a given position. And then you have heat losses to the wall and quenching of radicals. So this is a given parameter. So and now we can have superimposed flow. We can have endurance burning flame arresters. So flame arresters, where on top of these we can have a steady flame. So it should be then of course avoided that from the top the lower element of the flame arrestor reaches the auto ignition temperature of the mixture. But as there's a superimposed flow from the bottom to the top, this helps us. So this joints can be larger than the quenching distance. But we also can have a flow which is of course not helping us. So when the flow is in the same direction the flame wants to go, first we have laminar flow, then we reach transition and we have a turbulent flow. And somewhere here we will find a minimum value. And the MASG apparatus, which I've shown you, tries to mimic this complex behavior. So with a lot of work, they have the opinion to find a proper apparatus to get the really minimum value here. So and then if it becomes too turbulent, that means our hot gas which leaves the gap has a high velocity, mixes very fast with these surrounding atmosphere and maybe too fast. So then the cooling is dominant. So here velocity helps us again. So the gap can increase again. So this is a simple sketch how this quenching effect depends on the flow situation we have. So of course you see depending on the application, we have to focus on different main criteria. So then such an endurance burning flame arresters you can see here. So this, for example, sits on top on a pipe. So that should be breathing on the pipe, or tank, sorry. So the tank is in the sun, so it heats up, it cools down along a day and overnight. So there has to be a pressure relief to the outer atmosphere. So inside the tank we always have the surrounding pressure. So such an endurance flaming burning arrestor, so it's open to the surrounding. Here is a cap to protect against weather, and so it's open here and here, so it can breathe here, so the flow can go this way or this way. And what of course should be avoided, so if it's breathing outside, there is a possible explosive atmosphere on top of the tank, and this can be ignited. And of course this flame should not go in the tank, which would be a catastrophic failure. But of course what we have is there can be a steady outflow out of the tank through these flame arresters, so we can have a steady flame here on top of this arresters. So here the flame is burning, and so the temperature at the lower part of this flame arrestor element should never reach the auto ignition temperature. So it's a question of how much heat is transported away from the flow. This helps us here, so we can be larger than the quenching diameter. But of course then heat transfer in the construction is of importance. So if we have to avoid heat transfer or minimize heat transfer from top to the bottom. And you see here in quite complex geometry where we use classical crimp wire flame arresters. So where we have two bands which we put together, and where we have small triangular gaps, and so the flow in this direction is optimized. However, also the heat transfer in this direction is optimized. And here we have an element of sintered fibers, and you see it can be much smaller, and we only need one of these elements. So the advantage is the heat transfer in this case is much better to the left and to the right, and the heat transfer from top and bottom is worse or better in this example than here. We can have end of line arresters. Okay, this we have discussed. So where we have to avoid just the flame transmission. So we don't have a steady flame on top of such an element. There's just an explosion coming from the outside, hits the element, no flame transmission in this way, or more often occurring the other way. So the explosion comes from here, and here outside we have our chemical plant. Of course, the explosion should not come from here to the outer part of this pipe. So end of line arresters deals mainly stop the explosion in one way. We already need a gap width smaller than the quenching distance, because we have a superimposed flow in the direction of the flame. So which then supports the flame. And here, when we come to this turbulent region, we have the flame enclosures. So I will show you an example with a gas sensor here, how we can optimize configuration here. So a gas sensor should breathe, of course. There must be some gas entering the gas sensor, coming in contact with the elements here, where we measure the amount of combustible we have in the atmosphere. So breathing must be possible, but if an ignition takes place here, it has to be stopped here. There should be no flame transmission from the inside to the outside. And here we see this element of the standard apparatus to measure a maximum experimental safe gap. So we have a small vessel of several cubic centimeters. There is a larger vessel around this part, and we have here flat gaps, circular flat gaps, and we can then adjust the width of the gap. And here we ignite the mixture, and we check if there's a flame transmission, yes or no. And this apparatus is optimized in a way that we hopefully find the smallest value where we see or don't see a flame transmission. So this so-called maximum experimental safe gap. So how does it look now in reality? So after discussing all the theoretical details, here we have our flame arrestor for endurance burning tests. So and how does it work? So here we have a tank. We have an inlet here, so we can have a steady gas flow, which can be adjusted, of course. Of combustible, it depends on the requirements concerning the specific flame arrestors where it should be used. And then this vessel here is closed, so the gas flows through our flame arrestor here from top to bottom with a given velocity. And then we will start the test. So we ignite the mixture on top of this flame arrestor and check if there's a flame transmission from here to the inner side of the tank. Here is a pressure relief element which then opens, so we can clearly see has failed and can stop the test. So what we do during such a test, here we see 1, 2, 3, 4, 5, 6, 7, 8 positions for thermocouples. So we just enter some thermocouple elements to see how the temperature is developing during such a test. And what we are really interested in is, okay, at position 1, here we have the steady flame. And of course, we are interested in the heat transfer from here to here. So at which time we reach which temperature below, at the lower part of this element. And the second interesting part is there a heat transfer in this direction? So how is the temperature profile on top of the surface and then at this position here? So, and you can see the outcome of such a test. So you see here at position 1 and 2, we get a maximum temperature of 600 degrees Celsius. So the test takes some time. We're talking about minutes here. And you also see that here, figure 3 is here on the position 3. We reach 250 degrees Celsius, which is in the range of the outer ignition temperature of the N-hexane we have used here. But of course, so we haven't had a failure, but here you see The disadvantage you may see here, the small gaps we have. Again, these are gaps going this way, so to have optimized flow in the case when we don't have a flame existing here. And so therefore the heat is transferred perfectly in that direction. But the bigger problem is here the screw. We always need such a screw to fix such an element. And of course here we have perfect heat transfer from top to the bottom. What I have not mentioned is, of course, we adjust the flow rate to find finally the maximum surface temperature. So if the flow rate is too high, the flame will lift. So it's colder on top of the flame arrestor. And if it's too slow, the flame will move into the flame arrestor element. First quenching appears, again the temperature will decrease. So always we have to adjust the flow velocity to find the maximum surface temperature, and then we can perform the test. So how does it look like at optimum temperature? So here we see we have local lift up of the flame. So here we have the flow rate where we yield the maximum temperature. You see here the red glowing. So the chemistry takes is taking place directly on top of this flame arrestor element. So the maximum temperature is reached. And then, of course, it is a question for us, how does this heat transfer goes from top to the bottom. So, okay, how can we optimize such an setup? So I said you can see here the small triangular gaps we have. Perfect for flow and mass transport, however bad for heat transfer because it's going in the direction we don't want to have. And we need, which is visible here, at least 2 flame arrestors elements for this configuration. So one is not enough. When we just have one, there will be an reignition below the surface. So it's also expensive. So can we optimize it that we finally have only one element? So here this breathing I have explained to you, and this design I have explained to you. So the question is now, how can we stop the flame here, and how can we optimize the heat transfer? So here I show you the test setup. So now we have a pipe here, which is then also filled with our mixture, and this is open to the top, so there is no pressure increase during the explosion. So we always have around atmospheric pressure here at top of the head, so there is no superimposed flow going in this way. So here we see the overpressure. So we have a quenching of the explosion. So we have an explosion outside. It comes to the flame arrest element. It has to be quenched. So we have for a short time a superimposed flow, and then we have this fire on top of this element for a longer time. So here you can see an image of such a test. Here we have the explosion outside in the tube I've shown you. So the flame arrestor and everything is in range of this fire. Then this explosion stops, and here we have a steady flame on top of the flame arrestor element. So now I talk again about superimposed flow, but I'm on the other side. So in this time, we have a flow in the direction where we want to stop the flame. So the explosion occurs here in the inner part, and we want to avoid an explosion of the outer atmosphere. So we are in this turbulent region. So we are slightly larger maybe than the MASG, but we are clearly near the MASG value. And I show you the test setup. So we have a small explosion vessel. So this can be closed, and we can prepare proper mixture. Here we have a tank where we have the mixture, so we can evacuate this system here. And here we see the test sample. This is then also be evacuated. And then we refill our vessel and test sample with combustible air mixture. And here you see this set up in detail. For this specific configuration, we also have gas inlet and outlet, so we don't have to use this vacuum possibility. We can fill it directly with gas mixture. Here we have an ignition source and spark plug, and we have a pressure transducer. And the interesting element sits here in front of the vessel. So we have an explosion inside, and the question is, does the flame move through this porous structure? Is there a flame transmission, yes or no? And here you can see again such a crimped ribbon element. So for hydrogen, very small holes are necessary, but you can buy this in the market. And here we see some OH lift experiments. How does this flame transmission occur? And so when here we look from the top, from the bottom, so the flow is going in this way, the hot gas is coming towards you. And here we look from the side, and so we don't see a specific failure here. So, but then the flow in a specific distance has ignited. So below this flame arrestor element in the flame. In this case, we see only hot gas, and no flame transmission has occurred. With flame transmission, we can see here that there is a specific ring where the flame can move through this flame arrestor. So, of course, we have here very thin holes. We have maybe here very thin holes. In this area here in the middle, we have larger holes. That's due to the construction. And so you can see here where we have the larger holes, a flame transmission can occur, and this then ignites our surrounding. Now we look at such a sintered fiber element. So we have very thin metal fibers sintered together. So we have a porous structure. Of course, there has a flow possible through this structure. And with no ignition, we can see a lot of chemistry taking place. So there are, of course, always some larger spores. And then at these larger spores, we see some OH. So there's, of course, hot reactive gas leaving our porous structure. But in this case, no flame transmission can be observed. And so the question finally is, so what is happening here? Of course, this can fail too. So I have shown you here the ignition cases, because the big difference here is there's always something like a bigger spore. So in the further example with the crimped rim element, you have seen there's a large area where flame transmission occur. Here we have to focus more on the bigger spore. And this is one of the mandatory tests you have to perform if you want to produce such an element. So you can check the outcome, and then maybe you just replace this element here. There's another critical topic, and that's ignition at the hot surface. So here we see the pressure in two vessels, vessel 1 and vessel 2, the small vessel we have seen and the larger one. And if there is a direct flame transmission, you can see an increase of pressure in vessel 1, decrease again, and then you see the increase of pressure in the second vessel. So the pressure increases up to the explosion pressure. There's also a backflow into the smaller vessel. So here finally you also reach a higher pressure. And this takes place within in several milliseconds, so very fast. So it's a direct flame transmission. But we also see this effect here, that we have an ignition in the first vessel, and for a long time nothing happens. And then suddenly it ignites in the second vessel, and again there's a backflow increasing the pressure in the first vessel. And this is due to the fact that we, of course, have a hot surface. And the ignition position is now at the hot surface. Here, the ignition is somewhere in the flow, which leaves the nozzle. So direct flame transmission, here the ignition is directly at the hot surface. So there's a second optimization parameter we have to consider. So when we look on such an ignition by a hot turbulent gas, so this we have seen already. So we have a typical outflow. Here the explosion starts. Here we have a nozzle, and then we have a hot jet leaving this nozzle, mixing very fast with the cold surrounding atmosphere. How does this influence the ignition event? So here I show you some experimental results. Here we see Schlieren experiments, and here we see again OH-LIF images. And here we have no flame transmission, but of course there is a hot gas flow leaving our sample. Here we have a nozzle, so there's one specific hole, so we see the hot gas. Here we see already such a large jet leaving our element, and we can look into these jets with OH-LIF. So we try to excite OH radicals if existence, and we see them. So maybe you can see here in black. This gives us the surrounding of the hot jet, and inside this jet in the center we see radicals. It's hot exhaust gas, so there are always some radicals inside such a jet. But in this case the mixing with the surrounding was so fast it cools down and no flame transmission occurs. How does it look like when we have a flame transmission? So here again we see the jet. So here we see something like a Mach wave, so some compression in front of the hot gas, of the cold gas, and the cold gas is somewhere here at the top. Then here we see the hot gas, the hot gas is somewhere here. Here we see it again, slowly entering the lower vessel. So you see the time resolution is here 40 microseconds between each image. So of course it's quite a fast flow. And then we look with an OH-LIF laser into this hot jet, and in case an ignition occurs, we see a different behavior. We again see these OH radicals in the center of the jet. Of course, we see them, but also we see suddenly much brighter images at the tip of the jet. So in here, ignition has occurred, and this is a typical example. I have explained it to you yesterday with a numerical part already. So here at the side, of course, we have a very large shear. So the mixing here in this area is too large. There's mixing at the tip of the jet, but here at the side of the center, we have optimum conditions for reignition, and here it happens. So here more clearly, so here we don't see any OH in the center of the hot gas, but suddenly, in the middle of nowhere, our ignition occurs. So we don't have a Schlieren image here, but this is in this region of the center of the tip. So, and of course, this is a statistical process, so we can start it at identical conditions. Here we have just the outflow of hot gas. Nothing occurs. Here we have the ignition in a given distance, and I think here we have the ignition. No, directly it was two ignition locations, so it was really interesting. So it seems to start here at the top, somewhere here, and further away again at the center of the tip. So you see it's a very complex problem where we have to consider chemical reactions and different flow configurations. So there's still some work to do. But the main outcome is we have an ignition at tip of the jet. So then finally we come to this MESG apparatus where we hopefully have this optimized flow configuration to yield the MESG value. Again, we have a small vessel, a larger vessel. We ignite here, and we observe is there a flame transmission through this gap here, which we can adjust using a micrometer screw here. And like the minimum ignition energy, we use this to classify our combustibles we have into three different gas or explosion groups. So one important question is, okay, we classify our gases into three different categories. Is this classification, propane, is easier to handle than ethylene, always true? Or what is happening if we increase the pressure? Is there suddenly a configuration where maybe ethylene is more critical than propane? So this, of course, so we have discussed already. So now we see it as a plot of equivalence ratio. So hydrogen has much smaller MESG than ethylene, than propane. It, of course, depends on the mixture composition. Temperature dependency, we have discussed. The higher the temperature, the smaller the gap has to be. This pressure dependency we have discussed. So an increase in pressure reduces also, again, our safe gap. We need to stop an flame transmission. So I come to an end of this part. So you have seen, if we talk about something like flame arresters, flame-proof enclosures, flame quenching, it's a complex problem where we have to consider different flow configurations, superimposed flow and so on, where we have, of course, to consider the chemistry of the combustibles we have. So we are talking about an ignition event, and during ignition we have a very sensitive region, so a lot of radicals are involved, so it's very difficult to perform numerical calculations here with simple runs methods, for example. You always have to consider the complex chemistry here. And then, of course, we have an enclosure with complex inner geometry, and we have seen in the morning how this pressure piling effect can influence the explosion inside such an enclosure. So we do not have an empty enclosure, we ignite in the center and we have a spherical flame ball and motor. You have seen at the beginning, of course, there is a complex interaction of the explosion flame with the inner geometry, leading to eventually pressure piling, much higher initial pressures until the flame reaches the gap. So the size of the inner volume is of importance. So what kind of gap do we have? Have we a circular gap? Have we a flat gap? This is of course of interest. Then the length and the width of the joint, but also gas mixture concentration, initial pressure and temperature are of importance. So with this, I would like to end this session. Do you have any questions? Okay, so there are no questions, then we can stop for today. So thank you. Okay.